charge right where we need to go, we have to move the exact number of ions across the membrane. They can't count. So you overshoot the target to guarantee that you're going to be back at -70. Because all cells in your body have a very important pumping mechanism that I find students try to erase from their memories. And that pumping mechanism is the sodium-potassium pump. The sodium-potassium pump in cells is always working at low speed, okay? To guarantee that sodium is on the outside and potassium is on the inside. Which is why this takes a little while to get back up to -70. So the reality is, it's guaranteeing you're going to have this reaction. It prevents it from backsliding, but at the same time, it guarantees that you're going to get to -70 again. But it overshoots it. Because all chemical reactions that take place in you, regardless of whether it's your nervous system, your digestive system, whatever, you produce more than you need. Because if you're cheap, which our bodies are and our cells, you want to produce just enough. All right? But if you produce a little bit less than just enough, what happens? Nothing. Worst case scenario, cell dies. Oh, that's pretty worse. Yes. So by overshooting, going into the hyperpolarized area, it guarantees that you're going to get to membrane potential without needing to count. Okay? So, yeah. Now, you send a signal. But in reality, when you send a signal, you know, we're going to do an exercise. Okay? Take your hand, put up fingers, take your other hand, wrap it around a couple fingers. Just in contact. Right? Now squeeze. Squeeze. Squeeze till your fingertips turn purple. Right? Okay, I'm teasing. What's the difference between that? When I was just in contact versus squeezing. Both of those and everything in between, was I using the same set of muscles? Yeah, I was. And all of what was happening there was degree. Oh. Okay. So, let's try something else. Lift your hand up. Put it down. Lift your hand up. Put it down. Lift your hand up. Put it down. How can you do that? All right, you can stop. Lift your hand up means you have to get a series of action potentials to do this. But now you stop and put it down. Are you still getting those action potentials? No, you're not. Well, how did you stop them? This. Diffusion away from the synapse and degradation of the neurotransmitter. So what's going to happen? I mean, it's more complicated than that. It's diffusion, it's reuptake, it's degradation of the neurotransmitter. So what goes on is the molecule that's bound here, this target cell, will produce an enzyme that interacts with that and degrades it, breaks it up into components. Those components typically will be taken up by astrocytes or by the presynaptic axon. So the typical one that we all teach is the neuromuscular junction, where the neurotransmitter is acetylcholine. And the reason we teach that is the components are all simple. They're not complicated. Acetylcholine is a neurotransmitter. It's released. It binds. We have an enzyme that breaks it up. Acetylcholinesterase. It's an ACE. It's an enzyme. It's a big long word. It's acetylcholine, ester, ACE. And it's going to break up the acetylcholine into acetic acid and choline, both of which can be taken up rather easily. Okay? So degradation, diffusion, reuptake, all of those lead to the signal stopping. On occasion, people will have trouble producing too much of a neurotransmitter, not enough of a neurotransmitter. If I have too much of a neurotransmitter that I'm producing, the signal at the target is going to be overexpressed. So things are going to happen too much. If I don't produce enough neurotransmitter, I may not get the desired outcome at the target. If, for some reason, I make too much enzyme here to degrade the neurotransmitter, I don't see enough of a signal. Or if I have too many reuptake channels, I produce it, comes right back up, it's gone. We talked earlier in the semester. Is that a question or a story?
Oh, sorry, it's stage.
Oh, okay. I didn't want to miss it. I thought maybe, no, I'm not going to do that. Okay. We talked earlier in the semester. I said, you may all know or have some experience with somebody who's taking antidepressants. I mean, it's basically in our society, if I have 20 people in a room, 5 of them are either taking antidepressants or know somebody who is. It's a fact of life. Okay. Now, if they're really good friends of yours, you've talked to them, and they get really upset because they keep the physician, the neurologist or psychiatrist or psychologist, whomever, keeps changing their medications. And it's like, okay, this guy's making $874 an hour. Why can't he give me the right drugs? And the answer to the question is very complicated. Are you not making enough neurotransmitter? Are you making too much neurotransmitter? Are you releasing an appropriate amount? Or do you have too few calcium channels? Do you have too many reuptake channels or not enough? Is it a big sloppy synapse and everything is diffusing away? Or is it a small tight synapse and when you release the chemical, all of the targets are bound? Are you producing too much enzyme? Oh, there's a drug that targets every one of those. Oh. You know, the individual, we see the outcome, which is depression. But that outcome could be due to 11 or 12 different events happening at a synapse, which is why I insist you know and understand a synapse. Because if you understand a synapse, you will understand neurotransmission and neurological problems a lot better. Okay? That's why I go through this with you. Yes?
So, like Parkinson's.
Parkinson's.
So is that too much?
No, so Parkinson's. In Parkinson's, one of the first symptoms we see are tremors. Okay? We all know Michael J. Fox, maybe. Actor. Yes, maybe? Okay. He was in a TV show. I don't know, he was like a PR guy for the president or something. Spin City. Great. When his symptoms started showing up, and he started to tremble, he was getting tremors. And he figured out a way to stop his tremors. beautiful, actually. And he incorporated it into his character. Any of you ever watched Big City? As the program progresses, his character is talking, and he'll be at the desk, and he'll do this. Slap his hand down. When he slaps his hand down, he stretches his arm. And when you stretch a muscle, it stops twitching. That is brilliant. So in Parkinson's, what happens? We're going to try something else. Okay, we're going to do this. Okay. Obnoxious. Can you tell me what you're doing? By the way, that'd take you like an hour and a half. No. There's a lot going on there. Okay, you are kind of abducting and medially rotating, and then you are, oh God, it just goes on and on. Muscles are contracting and relax. So we have muscles pulling you out. These are relaxing, and then these start pulling, and these, oh, it goes on and on. But the important thing is, once again, going out and coming back is pretty much the opposite group of muscles doing similar things. Once again, going back to little kids. Ever watch a little kid when they learn to drink from a cup? There's a cup sitting there. They're just learning. Now, I give you a cup. I say, okay. I say, I'd like you to reach out and grab your bottle there and take a drink. You don't have to do it, but you can pretend, okay? Yeah. But the little kid reaches out, boom, and the cup goes flying. Have you ever seen that happen? Happens all, especially when they're first learning. Why? What's going on? Why can't they just reach out and grab that cup and take their drink? Instead, they go, ching! They go to pet the cat. Okay? You know, you go to pet the cat, you go, oh, nice. They come up there, why? What's going on? It's perfect. Believe me, your question is a very complicated question, which is why we're petting cats and knocking over water bottles. What's the difference between reaching out and grabbing that water bottle and reaching out and knocking it over? What?
You didn't stop.
You didn't stop, but let's say you stopped at the, so I go, ding, and I hit it and it goes flying. But I did stop. Control. It's all about control. This is control. This, hitting somebody, backhanding them. Same motion. Same motion. Different amount of control. In Parkinson's, to get back to the question, as you do this, what you don't realize is that this is a whole series of small motions. Ding, 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 that you have control over. In Parkinson's, you lose some of that control, so that instead of this, you get this. You get the trembling. You do little indistinct, or sometimes very distinct, movements to their extreme. So I do this, 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 and it comes out as this, trembling. So we're going to look at that in pretty good detail, because the way the signaling path gets screwed up, the reality is in Parkinson's, you're losing neurotransmitter production. Initially, you lose production followed by death of cells. And we're going to look at four different pathways involved with four different neuro or motor issues that can look very similar, but they occur at different parts of your brain. So, yeah. All right, I want to leave the synapse. This was a review that we never did early in the semester, and I wish we had done it earlier. So, all right, plexes. Plexus, singular, plexes, plural. Plexes is the root that we see in complex.